The James Webb Space Telescope spotted a large object about 10 light years away moving toward Earth. The posts claim that the telescope captured the object changing its trajectory.
The James Webb Space Telescope has turned its gaze toward 3I Atlas, the interstellar visitor making its ephemeral swing through our solar neighborhood, and what it has seen so far is nothing short of remarkable. The data returned by Webb, particularly using its near-infrared spectrograph, NIRSpec, revealed a coma suffused with an unusually high concentration of carbon dioxide relative to water, painting a picture of a comet unlike any we have studied before. This distinctive chemical signature has stirred excitement and perplexity in equal measure, raising tantalizing questions about the origins, composition, and evolutionary history of this alien traveler. Before we start, smash the like and subscribe buttons for more updates. When Webb observed 3I Atlas on August 6, 2025, it captured spectral images spanning wavelengths from about 0.6 to 5.3 micron. Those images allowed scientists to decompose the light into its constituent colors and identify the chemical fingerprints embedded in the gas and dust surrounding the nucleus. The result? A coma overwhelmingly dominated by CO2, with a CO2 to H2O mixing ratio of around 8.0 plus stars 1.0, one of the highest ever measured in any comet. In addition to carbon dioxide and water, the spectra also revealed the presence of carbon monoxide, CO, carbonyl sulfide, OCS, traces of water, ice, and dust. The CO2 outgassing is enhanced in the sunward direction, suggesting asymmetry in how the comet is driven by solar heating. Such a chemical profile defies easy comparison with typical solar system comets. In comets native to our solar system, water is generally one of the dominant volatile species when they become active. Yet here, the water contribution is comparatively modest, hinting either at a suppression of water sublimation or an intrinsic carbon-rich composition. One plausible explanation is that heat penetration into the comet's nucleus is limited, so the deeper water ice remains too cold to sublimate as readily as CO2. Alternatively, 3I Atlas may have formed in a region of its parent protoplanetary disk rich in CO2 ice, perhaps near a distant CO2 snowline. Or it may have been exposed to radiation levels that preferentially eroded more volatile ices, leaving behind a higher fraction of carbon dioxide. Either scenario implies conditions quite alien to those that shaped comets in the solar system. Beyond composition, Webb's observations provide insight into the behavior of the coma itself. The spatial distribution of the gases is not uniform. The outgassing appears intensified toward the sunward side, suggesting that the side facing the sun is more active and driving stronger emission. Webb's spectral imaging lets scientists map these variations as a function of angle and distance from the nucleus, helping to build a three-dimensional picture of how gas and dust flow outward. This anisotropy may also reveal the orientation of the comet's rotation axis or the presence of localized active regions, patches on the surface more inclined to sublimate volatiles under solar heating. The significance of detecting mysterious lights in 3I Atlas does not reside in literal artificial illumination, but rather in the glow of its coma and the way that light carries encoded messages about its nature. The fluorescence and emission features in the spectrum arise as sunlight excites molecules, which then re-emit or scatter the light in characteristic wavelengths. That glow is not ordinary or easy to explain in many cases. It tells us about the physical state, temperature, density, and composition of the coma. In the case of 3I Atlas, the brightness and structure of the gaseous halo are far more prominent than initially expected given its distance from the sun at the time. Some early observations had already hinted that 3I Atlas was glowing and active at distances where most comets remain inert. Even before the Webb data, there was suspicion that something out of the ordinary was underway. This anomalous activity, commencing at large heliocentric distances, implies that volatile species with lower sublimation temperatures are at play. CO and CO2 can sublimate even in the colder outer reaches of a system, while water typically requires stronger heating. The fact that 3I Atlas showed a coma at quite a distance points to a body whose volatile inventory is skewed toward more volatile ices and perhaps an internal structure that permits those gases to escape more easily. It suggests that, unlike many solar system comets that lie dormant until heated closer to the sun, this one was primed to respond much earlier, because 3I Atlas is only the third interstellar object confirmed to traverse the solar system After Oumuamua in 2017 and 2I/Borisov in 2019, every bit of data counts. Each of these interstellar wanderers offers a precious glimpse into the building blocks of other star systems. Webb's ability to probe the innermost chemistry of 3I Atlas has transformed it from a mere curiosity into a comparative specimen. By comparing the volatile abundances in this comet to those in solar system comets, astronomers may begin to discern whether the architecture and chemical gradients of protoplanetary disks elsewhere resemble ours or differ significantly. The high CO2 fraction in 3I Atlas may hint that the pathways of planetary formation and cometary evolution elsewhere allow far broader chemical variety than we had anticipated. Another implication of Webb's detection is that we now have a method to more precisely trace the physical history 3I Atlas. The abundance ratios between CO2, Colorado, water, and minor species like OCS act like isotopic clues, enabling reverse engineering of the conditions under which the object formed and evolved. If 3I Atlas formed in a colder environment or closer to a CO2 snowline, or if it has been processed by radiation or volatile loss over eons, those histories might imprint themselves on the gas-to-dust ratio, the relative abundances of species, and the pattern of asymmetries in the Coma. The role that cosmic rays, stellar outbursts, or collisions played in sculpting its composition may gradually come into sharper focus. Webb's high signal-to-noise spectroscopy provides the kind of detail necessary to separate different models of its evolution. Moreover, the detection reinforces the importance of advanced infrared instruments in studying distant, dim, or exotic objects. Because 3I Atlas is far from the Sun and relatively faint, visible light telescopes struggle to capture enough signal, especially when trying to probe chemical features. But infrared wavelengths are particularly sensitive to vibrational and rotational transitions of volatile molecules, making them ideal for uncovering compositional secrets even when illumination is weak. Webb's sensitivity and spectral resolution thus make possible discoveries that could easily evade less capable instruments. As more interstellar objects are discovered, having observatories with this kind of capability becomes indispensable. Taken as a whole, Webb's observation of mysterious lights in 3I Atlas has elevated the comet from a fleeting interloper to a laboratory in distant space. That rare status gives it outsized influence. It becomes a data point for testing theories of planetary formation, cometary differentiation, chemical evolution, and the dynamics of objects ejected from star systems. The compelling mismatch between the CO2 dominance and the suppressed water signal forces theorists to reconsider how volatile inventories might differ between systems, or how long-term exposure to interstellar space might strip or alter compositions. The fact that 3I Atlas may be billions of years old and yet still harbor a volatile-rich interior raises deeper puzzles about how such bodies retain such materials over cosmic timescales. Because Webb's view is fundamentally a snapshot in time, it invites follow-up at various epochs of the comet's journey. As 3I Atlas draws closer to the Sun, its outgassing behavior may shift, new volatiles may begin to sublimate, and the Coma composition could evolve. Tracking how the gas ratios change, how the asymmetric emission patterns evolve, and whether more volatile species or dust components emerge will help clarify whether the early Webb view was special or representative. If water flux increases later on, for instance, that would suggest the limited water signature initially was simply due to thermal and structural constraint. If CO2 continues to dominate, it might imply a fundamentally different inventory. In this sense, the mysterious lights observed are not static phenomena, but evolving emissive signatures that carry the fingerprint of a dynamic object. These findings also sharpen the contrast between 3I Atlas and prior interstellar visitors. Oumuamua was enigmatic in its own way, lacking a detectable coma or classical cometary tail, and triggering debate about its nature, asteroid-like, comet-like, or even artificial. 2I/Borisov, by contrast, showed strong cometary behavior and some resemblance to solar system comets. 3I Atlas seems to lie at a different point on the spectrum, a comet with unusual composition and early activity. Its behavior suggests that interstellar objects might cover a broader parameter space than the few examples we have encountered. The richer the sample becomes, the more likely we are to discover surprises, and Webb's new dataset nudges us further into uncharted territory. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on the mysterious lights James Webb just detected inside 3I Atlas? We want to hear from you. Thank you for watching and see you next time.